This video is a continuation of the last video. We're going to continue to calculate probabilities using what we've seen in the normal model, but with just a slight difference. In the last video, we had women's heights as the basis of our example. Now we're going to look at a normal model without a context, and you'll see quite a few of these in the 6.2 homework in my stat lab. Part A says find the area in a standard normal curve to the left of point 63. So I know I've got a normal curve here. You can see that from my wording. I'll draw out my bell-shaped curve. Extends infinitely to the left and infinitely to the right. But it doesn't give me a mean and a standard deviation like it did before. And it doesn't have to, because this is the standard normal curve. In the standard normal curve, it's a normal curve with a mean of 0 and a standard deviation of 1, always. The standard normal for this class will always be 0, 1. So 0 is in the middle. I want the area to the left of point 63. So I've got my positive values to the right, my negative values to the left. Point 63 would be on the right-hand side. And I am shading to the left of this. And with this picture, now I can see what to input into my calculator to get my answer. I want the area. I want to know, well, what is the area of this curvy shape here? And to do that, I can use normal CDF. Recall that the area under this distribution function is equal to the probability. So when I want to find an area, when I want to find a probability, I'll get a normal CDF, which is under the second VARS menu. Number 2, normal CDF. My left bound, my shading starts all the way down at negative infinity. We can't plug in negative infinity to our calculator. We want negative E99. So negative, second comma, 99. My right bound, my upper bound, my shading stops at point 63. Because this is the standard normal, the mean is 0, the standard deviation is 1. So we get 0.7357 if we round to 4 places. So we've shaded about 74% of the curve. That looks fairly accurate. I've definitely shaded over half of the curve. Maybe this is about 74%, this is about 26%. So everything looks pretty good. Same idea in part B. Find the area in a standard normal curve to the right of 1.72. Standard normal is your normal bell-shaped distribution with a mean of 0 and a standard deviation of 1. 1.72 would be somewhere up here, and we want to the right of that. So to put that in my calculator, it should look something like this. And we get, this is equal to 0.0427. That seems fairly reasonable. I'm not a great artist here, but I haven't really shaded a lot of this curve. Had I taken the time to actually draw in the standard deviations, it would be more accurate, but definitely less than 50%, about 4%. Part C, so a little bit different in its wording. It says, find the probability that a z-score will be between negative 1.4 and 1.32. And z-score is my keyword here. Standard normal up above told me it was N01. Z-scores as we saw back in chapter 3, are associated with that nice bell-shaped curve, that normal curve, they are also to be on the standard normal. So I know my mean is 0, I know my standard deviation is 1, and I want the probability, which probability on the normal curve is normal CDF, is between negative 1.4 and 1.32. Draw in a sketch of this. Zero as my mean in the middle. Negative 1.4 would be somewhere down here. 1.32 be somewhere here. And I want the area between. So what is this area? And note, I don't go all the way down to negative infinity, so I don't have a negative E99. I don't go all the way up to positive infinity, so I don't have a positive E99. My lower bound is 1.4, or a negative 1.4. And my upper bound is a positive 1.32. To get my answer, hit second bars, select normal CDF, and input my left bound, my lower bound, my right bound or upper bound, and then 0, 1 as my mean and standard deviation. It's 0.8258. So about 82 or 83% of our observations should have z-scores between negative 1.4 and 1.32. Those aren't outliers. They're not 2 or above. Final question. Find the area to the right of z equals 6.55. So z is equal to 6.55. This is a z-score. So again, I'm on that standard normal curve. Again, it always helps me to sketch out what's going on. So 0, 1 would be here, 2 would be here, 3 would be here. 3 is an outlier, 2 is an outlier. So 6.55, that's way up the curve. And these tails theoretically go on forever. There's just not a lot of room on them, but 6.55 would be up here. And we want to the right of that. So my shading, if I do it in a different color, say yellow, would go all out here, be microscopic. Have hardly anything shaded underneath the curve, so I expect to get a very small answer. When I input my information, my lower bound would be 6.55. This theoretically goes all the way up to infinity, or E99. And then 0 for my mean, 1 for the standard deviation. And this is my answer. So I get 2.89, but it's times 10 to the negative 11th. So this would be a decimal point. Then 10 zeros. Then the 289,145. If you round that to 4 places, which you do in my style, it's just 0.0000. There's pretty much a 0% chance that you could find an observation with a z-score at 6.55 because it's such an extreme outlier. It's so far up the curve that there is a very small chance, but we would round it to be 0 in this case. So note the different wording of the same style of questioning. You've got z-scores as an indicator to use the N01, or you also have the standard normal curve to indicate that mean and standard deviation.